Okay, welcome back, everyone. So for those who are not in Toronto, like yesterday, we had this beautiful day with weather with sun and was it 15 degrees Celsius or something like this, where you could go out without a jacket. And today, of course, it's snowing. So that's probably when you come to Toronto in March and April. Oh, March and April, then that's the weather you get. Okay, so I will come to what I want to do today. So I was just finishing off one result that I kind of didn't have time to do last time. And then I really want to start talking about some more metric geometry. Right, so maybe I just get started with this. So last time we proved this kind of general monotonicity theorem. So essentially they're saying that you have a continuous function, then from R to R, then you can throw away an over-dense set, and outside this over-dense set, on each connected component, you're either strictly increasing, decreasing, or constant. And so now what I want to do is to somehow do some kind of differentiability result similar to what we have for o-minimal structure. So the statement here is the following. So fix a k, that's the kind of degree of differentiability, let f, and so I will just do this in let's say maybe I, so that I indicate that it's an interval. So this lives in R, some interval, maybe open, maybe the whole thing, maybe the whole real line, and you take a continuous functions. So again, this kind of, as I said last time, we always want to prove this kind of theorems in further generality, but for now, this is kind of the best thing we have. So we just have the talk about continuous function. You would hope that in general you would be able to talk about functions definable in an open core of an expansion that does not define the integers or type A. So then what this says is that then there is and nowhere then set V subset of, I called it I, such that F restricted to the complement is CK. So to remind you of the kind of the general assumption we have is that we work in an expansion, in this case of the real field, that does not define Z. In the previous proofs, I mean, really there was if you want to prove this for type A expansions, so things that do not define a dense omega orbital set, but you want to throw away multiplication, that's all something you can do rather easily. So the proofs vary or more or less the same. In this setting here, though, it's substantially easier to prove this result here in the setting where you have the multiplication, simply because, and this is hopefully an easy exercise, something that you learned in the o-minimality courses, that if you have multiplication, then defining the derivative is rather easy, which is rather hard when you don't have multiplication. But it's true in both cases, but this requires both in the o-minimal case and in this case for the work. So I will really do prove this one here really just for the case of the fields, and really just unary case, but this is not too hard to express. Okay. So we prove this by essentially by induction on okay. The k is fixed, so the induction, we want to induction on n, and this runs from 1 to k. And we want to show that the kth derivative is essentially continuous outside an over-dense set. Okay. So suppose by induction, the ith derivative for I smaller than n is outside some fixed, some over-dense set. I should have written this the other way around. Suppose that there's nowhere then set, so that all these derivatives until n are continuous outside this nowhere then set. Okay, and so now what we want to do is we want to get the next derivative. So what we do is observe, first of all, that as I pointed out, because the field is definable, all these derivatives are definable. Okay, and so now what the so now really the thing is that what we have to show is so if the function is differentiable on some open set, then the derivative is definable, by the way around. And so what we now want to do is we want to do the next step. And so we now want to get the kind of the nth derivative. And so what we can do is, let's note that by the monotonicity theorem, there is increases nowhere then set, there is nowhere then set v1 containing v0 such that the n-1th derivative is what is it, either strictly monotone or constant on each connected component of, now what's I set minus v1. So and each constant, if it's constant, and of course it's very easy to define the I mean then the derivative is if of course continuous, but that's kind of not the not the hardest case to get. So the case where you're interested in is the case where this n-1 derivative is strictly monotone. So the next thing we want to do is we want to use this monotonicity, and by Lebesgue's differentiability, Lebesgue's differentiability theorem. So this is really one of these kind of classical differentiability theorem. We know that since it's now, we can assume that it's strictly monotone on all these connected components, the set of so that is n-1 is differentiable at x is null, right? That's the back null. Okay. Yes, so it's yes, one of the other. Thank you. Okay, and so now the one of the other results what you have is that the derivative of a differentiable function is their class 1. So by the theorem we had before, you know that this is continuous outside a nowhere then set. So I actually need, okay, anyway. So is that what I want to? So there is nowhere dense set V2 extending V1 such that Fn is continuous on this on the complement. So U set minus V2. That's what I wanted to show. Okay. Okay, so you get differentiability for this so CK differentiability for continuous functions. Okay. Okay, that's all I wanted to say from fixed up from last time. So really now what I want to do is I want to come back to metric geometry. So let me maybe start. Well, I can continue over there, and it's easier. So this is now the maybe fifth and final chapter of what I wanted to say about. And I want to recall something that we talked about when we talked about dense omega orderable sets. So we had all this kind of, and we improved the the strong bare categoricity theorem. So we had this, remember that when we had a compact set, or I mean, really it was enough to have a nowhere dense set. This was this R. So E compact. No interior, empty interior. And we had this idea of taking the complementary intervals and taking the left endpoints of this complementary interval. So recall that we introduced L. This was the set of all left endpoints of complementary intervals. And so what we observed back when we talked about this was that you could order them using omega order. So we defined this omega order. Remember that this omega order essentially came from the fact that we ordered them according to the length of the mid of the complementary intervals whose endpoint they were. Okay, and so we got this was here an omega order. And this omega order, and not only is this an omega order, well, it's not necessarily a dense omega order in the sense that we defined this left endpoints, they lie dense in this Cantor set C, in this kind of compact set without interior. And so what we're going to do next is somehow remember that the problem always was is when we had a dense omega orderable set. So the last thing we have to somehow always do in order to get something somehow wild, like defining the integers if we work over the field, is to take this set L and move this somewhere dense. Because if you have a function such that some power of L is somewhere dense, then we saw, this was one of the things that we did, is that you then can find a new omega order such that this set here is also omega ordered. You always get this from the old omega ordered, but then you know it's dense and everything, and you define the integers or your type C or type B in the case if you work over the additive group. Okay, and so now I really want to talk about this. Finally, talk about this connection to metric geometry. And really, here's the point that what we want to do: add some further assumption on C, such that we can find this set F, such that that maps this kind of left endpoints to somewhere dense. And the kind of the magic of all of that is that that metric geometry really gives us very nice condition for that using metric dimensions. So the metric dimension that I going to use is essentially the one that I introduced, and Hausdorff dimension. So Hausdorff dimension I will not introduce, except I will use this as a black box because it's so hard to compute. But I will compute more things with upper Minkowski dimension. So for the two notions of metric dimension I will talk about is this, as I said, Hausdorff dimension dimension and upper Minkowski dimension. And really this will be dim H, and this will be M. And for how the upper Minkowski dimension I will define again, and that I already looked at. What you need to know, I think, for Hausdorff dimension is essentially stuff that I will mention on the fly. But maybe one thing that you should remember is definitely that Hausdorff dimension is somehow always bounded above by Minkowski dimension. So Hausdorff dimension is in particular 0 uncountable sets, while the upper Minkowski dimension is not. What you will see in a moment is that it's much easier with Hausdorff dimension to produce, Hausdorff dimension satisfies stronger projection theorems, which I will state in just a second. That makes us much easier to find this kind of map F. One thing I do want to point out is that, I should write it like this, because equality can truly hold, is that on the other side, we'll always have this kind of topological dimension, or this naive dimension, that's what I called it. So this is really kind of, if you have the dimension you know from o-minimality in some sense, which is, at least that's the only one I'm really going to use, is that the dimension of a definable set, let's say, or any set X, is a maximum M, such you can find a coordinate projection from R to the M, such that the image under this coordinate projection has interior. Okay, so if you prefer other, so in general, this is always lower than these metric dimensions. If you prefer other, like there are many notions of topological dimensions, so like Lebesgue's covering mentioned, inductive dimension and so on. In this case, they will all coincide, although that's not non-trivial to show with this dimension here. But for the kind of, to keep it simple, I will only talk about this topological dimension, or this kind of naive dimension coming from o-minimality. Okay, so now really what I want to state is the result, in some sense purely in metric geometry, which is a kind of, I think, a consequence of the mass-run projection theorem, which I will at least say what it is. And so the idea is really that if you're here in the room, I'm going to move over here, that what you want to do is I want to say, if I have something, if I have that C is positive Hausdorff dimension, then you can always find this F. That's what I'm going to do now. This is essential. If C is positive Hausdorff dimension, then you can always find this F that maps this kind of omega orbital set to somewhere dense. And this really will follow quite easily from known theorems from metric geometry. This really is the lemma I'm going to state is actually from a very nice paper of Jerry-Edgar and Chris from 2001, which, well, per se, I don't think has some direct connections to the Tameness program, but Chris might correct me later. But really, where this kind of construction of this function first appeared as some kind of rather easy lemma, which I'm going to prove in a second. So suppose you have, I should let E be a subset of R, no mentioning of definability or whatsoever. And then if you know that the Hausdorff dimension is positive, again, don't worry about if you don't know precisely what Hausdorff dimension is. We'll use one theorem about this, and you can take this theorem as a black box. Then there is N in N, and an linear function. I will say about what I mean by this function, the word I mean by linear here, T from R to N to R, such that T to the En has interior. I'm going to give a proof of this, and I want two things I want to say. Linear here means, I mean, we have to be careful as logicians. It means R linear, so it's really the kind of the scalars come from R, not just from Q per se. And so really now let's see what this means. So we have this set E. If you look over there, this is the Cantor set. Then we have a linear and particular continuous function such that the image under this power here has interior. So if you now have a set that lies dense in E, like our omega orbital set, now then you map this under this T, then the image then the image of this omega orbital set will be dense in this interior, and you have a dense omega orbital set. Okay. So I'm going to prove this now because it's such such important and also in some sense easy corollary of what's called mass projection theorem. So the proof is as follows. I think I should move this up a little bit, otherwise you don't see. So the proof, let's take, to make it simple, let's call D to be the dimension of E. And so one of the things that one has to somehow believe that is that if you take higher and higher powers of E, so higher and higher Cartesian powers of E, then the dimension increases. So let's take K in N such that K. Yes, thank you, Lau. Yes, the house of dimension, yes. Thank you. So I got it. So I take K large enough such that K times D is larger than 1. Okay. No need to know anything about house of dimension in order to be able to do that. But then, and this is kind of one of the things I will use about house of dimension, is it's known that if you take now the house of dimension of the kth Cartesian power of E, that this is larger or equal, not necessarily equal, K times D, and hence in particular larger than 1. Okay. I'll move this up. Okay. So now we can use what is called the mass projection theorem. That essentially says that if you have some set in some higher dimension, so this lives in R to the K, and this has large Hausdorff dimension, then if you take essentially almost every projection you take, any other projection will pick up positive Lebesgue measure, positive Hausdorff measure, one Hausdorff measure. So that's essentially what the mass projection theorem says. With whatever direction you project into, almost every, in terms of measure, almost every projection will give you positive Lebesgue measure. So there, what this is. So everyone on the line. Yes, sorry. Yes, I mean this kind of, if you would project between, let's say, R to the N and R to the M, you would have to say something like that. The projection would pick up enough of the dimension, right? I mean that's what it would really. Well, to make this a little bit more precise later on when I talk about higher dimension and for the other dimension. But really, what this says is, I mean, when really, if you're really careful, I don't going to do this here. It's really this thing is that, I mean, you have the Grassmannian for the projection onto from R to the N to R to M. You put a measure on it, and with respect to that measure, almost all the projection will out. So then there is, as I said, there are many, but we really just want to have one. Then there is an orthogonal projection, not necessarily a coordinate projection. And this goes from RK to R such that, and now the image under this projection of EK has positive. Mass. I think this is. I mean, this is a special case. I think of the Marstrand projection theorem. There's a whole industry, and I will mention one of these results about how fractal dimension or metric dimension behave in projections. And this here was a kind of the classical first result for Hausdorff dimension. Yes, as positive Lebesgue measure. And so you can make this precise. So this really, as Chris pointed out, about projecting to dimension 1, but this you could make this for projection between r to the n and r to the m, and then this would really say the house of dimension is large enough, so you don't lose out. Okay. I think our former colleague of my former colleague, Bob Kaufman at he at Illinois, he gave one of the, I mean, not the, he didn't prove Marston's projection theorem because it's called Marston's projection, but I think he gave one of the first more understandable proofs of the Marston projection theorem. Okay, but so I'm still not finished yet. So I want to get this kind of function t here, and so I want to get from Lebesgue measure to interior, but there is this kind of, again, classical result. I think this is due to Steinhaus, is that now if you take the sets of differences of a set with Lebesgue measure, positive Lebesgue measure, then this has interior. I think this is Steinhaus. Early last century. And so then when now you put this together, so now you take, let n be 2 to the k and t from r to the n to r be the composition. So this is t of x1 to t of xn would be really just if correct. Yes, if n is 2 times k, this would be projection of this would be, yes. Really just pick one projection. So yes, I mean, so to be concrete, you just need one of them. But as I tried to point out, I mean, almost all of them work. So this is really, I will always, we'll talk a little bit more about projection theorems in just a second, and this will always be for almost all, but really the case we will consider just one. Okay, and so then we get as an, maybe this I do want to keep. So. So then really what we get as as a corollary is that, so if you have one of these, I mean, maybe I not write it C so that it's clear. Okay, now again, we work in an expansion of the real field now. It does not define Z. And you let C be, what do I need? Well, let's do it with a, always take the closure, but be compact and empty interior. Yet the house of dimension is positive. Then if C is definable in this expansion, no, okay, so if I assume that, then C, now I've screwed it up a little, but I think the statement is correct, that C is not definable. Really what I wanted to say is that if C is definable, then R defines the integers. And the proof is really now, as I pointed out, observe that as above, L is an omega order dense in C, so where L is a left endpoints, it's written up there, and now note that I take what did I call it? T, probably T as in, that should be 5.2, and this was 5 as in 5.1, then T of L to the N is a dense omega order. And then hence, if that is true, Z is definable by one of the earlier results. Okay, and so this is how you get this from how you get, if you have a set of positive Hauptwürmer dimension, then you get this for you get that it cannot be definable unless the integers are definable. I'm not going to go into this because I really want to stay over the fields and I want to talk about Aswad dimension. You can show that the same thing works, not over the real, okay, not necessarily over the real group, because you have to be a little bit careful here, because see, this T is linear, but we said over there this T is R linear, so the kind of the coefficients in this linear map might come from R and not from Q. So in here, this T might not be definable. However, if you, instead of looking just at the additive ordered group, you do look at the whole real vector space, so we have scalar multiplication by every real number, then this T is definable. So in that setting, you can do the same thing as here. So if you work over, if you replace this assumption by does not define Z by type A, and you go to the real vector space and get the real additive group, then the same conclusion holds. Of course, sometimes you might be lucky that that this kind of projection, this linear map here, is actually has rational coefficients. For example, I think for the usual ternary middle third scatter, that's probably true. But I mean, the rationals are countable, so they might actually lie in this exceptional set of measure 0, where we don't know whether the projection satisfies the conclusion that we have. Okay, yes, so that's what I want to do. The end disc, I mean, this can be done. It's actually not this easier in this case than what we're going to do later on. You can also do this, and we'll say a little bit more about this for sets in R to the N. But then you have to first of all make sure that what you're looking for is coincidence of dimension, or rather, let's say that they're not positive. Yes.
So in this Markov projection theorem, you cannot guarantee that there will be a phi with rational.
No.
Rational.
No. So it's always up to measure 1. So I mean, you have the kind of what is it? You take the Grassmannian of one-dimensional subspaces of R to the K. You put there you can put a measure on it, and so I mean, it just might be that all these kind of that you get by rational projections just lie in this kind of measure 0 set. So there's really no hope for them. Okay, so now what I want to come back to is really the. Did I lose the statement of that? No, I have it here. Yes. So, okay, so this is really everything about what I want to say about Hausdorff dimension. I'm now going back to Minkowski dimension. And the big point is that this master, why this is so much harder there, is that this master on projection theorem fails for Minkowski dimension. That's simply this kind of statement here that you can always, if let's say you have something of positive Minkowski dimension, this does not guarantee that you can find this linear map such that you get interior. So there we really have to do some work. So maybe I keep this, I go erase. Right. Okay, so just really because I don't expect you all to remember this for since last time I mentioned this, really what first the sorry, upper Minkowski dimension, I want to recall the definition of a subset E of R to the N is, I would say again, how you should think about this is the limit, the lim sup of the log, see this, log of, well, there are many ways of writing R as R goes to 0. And again, what this is, so this the N here of ER is the number of balls of radius R in the appropriate R to the N that you needed to cover E. And really, if I always think this, of course, then you have to know that this actually converges. But really, if this is of this form, so if the kind of the eventually the number of boxes that you need to cover E of radius R is proportional to R to the minus D, then D is a dimension. This is. Have to, of course, be a little bit careful because this suggests an actual limit here, but really we just take the lim sup. Okay, so that is one of the exercises I want to leave here is that, again, this is a really easy exercise. And if you really want to learn a little bit about these dimensions, maybe the easiest exercise you can do. And this is really where this kind of our interest comes in, is that if you take 1 over n plus 1, where n ranges over the naturals, you want to compute the Minkowski dimension of a, and this is 1/2. Okay. And I leave this really extra, but this is kind of crucial that for this upper Minkowski dimension, this doesn't have to be 0 on countable sets. That's what this is, because it's really clear that if you take the same thing here, let me write this like this, with Hausdorff dimension, I'll write this again, this is definitely 0, so it's clearly smaller. So this kind of Minkowski dimension really has the ability to distinguish between countable sets. And that's, of course, very crucial for what we want to do. Okay. And to be honest, I think it's much easier to compute. That's why I think metric geometers like it, and I like it, because if you have Hausdorff dimension, I mean, there might be the better theorems for that, but it's really tough to compute. Well, it's kind of easier-ish for this kind of dimension, because I mean, it's always the other name for that is, if you don't want to call it Minkowski dimension, is box counting dimension, because essentially what you're doing is you count boxes, and then you look how this kind of counting behaves as you go to infinity. Okay, so I actually worked this out. So there is, so the Master projection theorem fails, but there is a projection theorem, and I want to write this out since like this geometry part of this. So if this was 5.3, 5.2, then maybe this is 5.3. So now I want to state the projection lemma really for Minkowski, for this, for the upper Minkowski dimension. So you can see what you still get there. And the idea here really is, I didn't make this explicit with the Masterrand projection theorem. What you can do here is that you have a subset of R to the N. And so now you can find, then there is T from R to the N to R to the M. So this is again linear meaning here R linear, such that well, you not get in interior, you get the following. You get that the dimension of this projection is at least the dimension of E. Let's try to get this right. And then by some factor. So what this really says is that, again, very similar to the mass projection theorem, is that if you have a r to the, if you have a set in r to the n, this is its dimension, then you can find a linear projection or a linear map that the image at least has still this much of the dimension. So it might be a little bit smaller, but you still get a substantial part of this this dimension. And again, the statement I put this here is in the terms of there is a linear map. So really what this should be is that for almost every orthogonal projection, this happens. Okay, and let me move this up. And so now what you can do is the kind of, so really what we want to do is we want to take a subset of, in this case of R, take a Cartesian power of it and make sure that after we project it down, the dimension is high enough. So if you, maybe you do this on the new, it's kind of trivial calculation on some. So what we're interested in is in the special case that E is a subset of R. We're interested in the special case that is a subset of R. And we want to compute really, I mean, this is kind of, we want to find a linear map such that the dimension of, now let's write it E to the N. So let's say this is really what the situation we're caring about is, suppose we want to have, we have a set that has positive Hausdorff dimension, positive upper Minkowski dimension. And really what we want to do is we want to find an N and a map T such that the dimension of this one here is at least, I mean, as close as you want to 1, is at least 1/2. And so what I claim is that this projection theorem that we have here, that this actually can give you this to you. So if you, so now suppose that, I mean, we take an N, we take one of these projections, and then it will look like how this whole thing here will go when we grow, when we let N go to infinity. So let me make sure that I got all these right. So this is really larger or equal to the upper Minkowski dimension of E to the N. And so sorry, I should also say where this T goes, and we always want to project it down to R. So in this case, the M we have up here is 1. So this is then larger or equal to 1 plus 1 divided by 1 is 1 over N dim M E to the N. And so now for Minkowski dimension, it's one of these things, but that's you can convince yourself is that if you take the Minkowski dimension upper Minkowski of E to the N, that is actually, because it's such a nice box counting, N times the Minkowski dimension of E. So this will be equal to, I'll write this, getting low here, sorry. So this should be then N times dim M of E plus, and you move the N out here, so that should be 1 plus N minus 1 if you multiply this in. Okay, and so if you then multiply, divide by N is probably what you want to do. then you get 1 over n plus 1 minus 1 over n in ME. And so now if you let, hopefully believe it, if you now let n go bigger and bigger, then eventually for a large enough n, this will be larger than 1/2.
For sub t.
Yeah, for some, so yes. So
Depending on n also.
right. So for every n, we can find a t, and then we get this. Let me move this up. Sorry. So now I can state finally the result I actually wanted to prove. Really do some geometry for change. Yeah, so that's where we don't need anymore. We just need this observation here. Sorry. So then I can move this up. Should be 5.2, 5.3, 5.4. So that this is in the paper with Anton, Giulio, and Chris. And so really what we now can do, I mean, I do want to is that let I think we want, because you have to be careful with Minkowski dimension, and the upper Minkowski dimension of E is positive. So then there exists, and this is essentially what we showed, but we want to do something slightly stronger. Then there exists n. This is the argument we did, and linear TR to the n, such that, okay, would be awesome if this is true. I will change this here. It is dense in R. So it would be great, similar to house of dimension, if we could get this kind of linear map, such that if you apply it to a power of t, you get interior, or at least that you're dense. But as I kind of tried to point out with this projection, the only thing that we really get is that the Minkowski dimension gets larger and larger and larger. And we're really not aware of any kind of function, and I hope that actually that is true, that is linear, that gives you something like this. However, so we're working over the field. So we really have polynomials that we can use, and particularly division. So what we want to do here is we apply to this T of E to the n, we apply Q, where Q is the following. And then the statement is true. So where Q of any set X in subset of R is really taking difference quotients. So where x1, x2, x3 are, x4 are in X, and of course you need that x3 is not equal to x4. Okay, so remember that for what we did for Hausdorff dimension was that we took this kind of orthogonal projection that gave us something of positive Lebesgue measure. Then we used the Steinhaus result to get the difference, and then we get something that literally had interior. That's not enough here. So, but once we do this quotient, then we're ready to go. Okay, so really what I'm going to prove this now. This kind of that really what I have to do is now, if you have a subset, I mean, by this kind of argument about the projection lemma, we can assume that E has Minkowski dimension at least 1/2. So really that, I mean, the T allows us to assume that the Minkowski dimension of E is larger than 1/2. And the last thing I have to do is that if I have a set that is positive, the Minkowski dimension at least 1/2, is after I apply this difference quotient, that I then get something with then that gets something that is dense. So I didn't get this. So by projection lemma or by this kind of mark, you can find this exist n and t linear such that dim m of e to the n is at least 1/2. Okay. So now we show that. So now assume that the Minkowski dimension of E is actually larger than 1/2, and show that Q of E is dense. Okay, that's what I'm going to do. So erase this is kind of so. But when we originally proved that, we came up with this kind of really box counting argument coming from, and we used some kind of additive combinatorics. And then I think Chris showed this to Kenneth Falconer, one of the famous geometric measure theorists, and he wrote back with a really beautiful and really, I think, easy to understand geometric argument, which I'm going to give now. So that's really, following argument is really due to Falconer.
Half important, I mean, if it would be just bigger than 0.
Yes.
Would that be also enough?
No, no, you'll see in the proof in a second. I mean, you can, I mean, it's a really elegant proof. I think, I mean, maybe this is a good point. So again, the argument I'm now going to give for this kind of, for this substatement is really due to Falconer. I do want to point out, Chris pointed that out, this is for metric geometries, of course, they always say all these statements are about projection lemmas, they're about linear maps, right? Because that's what they think. They think about orthogonal projections. They never think about how these things behave under polynomials. So there's really, I mean, you would assume that something like this would be known, but I think this comes from the fact that really for them, they care about, they really don't expect this.
I mean, Falconer told me that flat out.
Yeah.
I asked if you guys came up with this limit, if this is true, and he said, we would never think to look at quotients of anything.
Right. And for example, there are these kind of, you can show that this kind of argument using the Master projection theorem can really work in higher dimensions and allows you to show that in a structure that doesn't define the integers, definable sets have the right Hausdorff dimension. And this is because the Master projection theorem works in high generalities. We really don't have an analog of this for higher dimensions. If I would allow you any polynomial. So I mean, that should be, I mean, that could be some kind of area of fractal geometry, but it's kind of, it's not, or not yet, or maybe never will, because they usually look at linear maps. Okay, so suppose not. So suppose you have suppose you have the something that has dimension larger than 1/2, and the set of difference quotients is not dense. So the first observation, this is, I think it's a really crucial observation, hopefully I can draw some picture, is that given E, what is Q? QE, what are really these difference quotients? Geometrically, this is a set of slopes of non-vertical, this is where you, because you throw away the difference is 0, vertical lines connecting points in E. connecting. So points in E square. Okay. All right. So then this being not dense means that there is a certain set of slopes between points that you do not have. I will draw this in a second. So that will give thus, I'll draw this and it becomes clear that if you take the difference between two of these points, this is essentially the kind of, this gives you the slope, and these live in U square, is disjoint from some open double cone let's call C is I said C, but C I'm using so well centered at the origin. Okay, so let me move this up and then I draw a picture down here. Okay, so the picture you should see, you're living in R2, that's where E square lives. And now you have this double cone at the origin. That's fine. You have this double cone at the origin. Yeah, oh, I don't know. And so you have that, and so what this means is that there is nothing that you do not have anywhere 2 points where the difference lies in this double cone. So this one here is does not contain anything as u minus v. Because if it would be, then I mean, you see that what this really says is that if you have something in here, the difference set, then the being in this double cone means that the slope is in some interval given by this double cone. Right. And so now what we're going to do, argument, so you take the line which is orthogonal to this cone. Let's call this L. So L, let me write this here. So let L be the line through the origin perpendicular, and should say orthogonal, perpendicular to C, to the axis of C. And I do want to point out, so that this kind of, I do want to point out this construction so far really doesn't depend on E so much. I think this is important, that really we take one interval that not contain, does not intersect QE. So we assume that Q is not dense, and this double cone corresponds to an interval that QE misses. And really the cone really in this case only depends on the interval you choose. So you could it's really, so far this construction is really just about the interval that QE is missing. That's the only thing you need. Okay, so Let me keep this, let me keep this, let me erase this. Okay. And to L. Okay. So now here's the observation. So now what you want to do, so maybe draw this here. So remember that E2 somewhere, E square somewhere lives here, right? I mean, E2 lives somewhere here in the plane. It's a small set, so it's really hard. I cannot really draw this, but you should keep in mind that this is where it lives. Then the restriction to E square of the projection of the orthogonal projection onto this line L is injective. And I'll go over to this picture again. Well, why is that? Because I mean, see, suppose you have, let's say you have a point, this point here, let's call it X in E square, and suppose there's something above it, Y, then the difference lies in this cone. So this would be here, the vector X, Y minus X. And so that's injectivity, and they get this for free from this kind of construction. But this is not everything. So what you also get is, so you know that it's injective, so that this has an inverse on here. You get that this is Lipschitz. Like, you can think about why it's Lipschitz and while I'm writing it. So, and the computational inverse inverse is Lipschitz. Yes, yes, I'm so sorry. Thank you. Yes, computation. Yes, I mean, so if you, the point, for example, you're here, right? You said this point X. Then we said that, so nothing, in particular, injectivity gave us, because essentially, when you move it over there, we land in the cone. So, but this also not only gives us the injectivity, it gives us somehow that nothing is allowed to be in this cone, right? If we move this cone down here, so there is nothing in here. So that means if you're close to X, I mean, that's what Lipschitz is. If you're close to X, you at most, that's the most you can grow. So there you immediately can, from the cone, again, read off the Lipschitz constant. So again, I point this out for later. So not only, so I said that this cone just depends on the interval that you're missing, that you chose, but not only that, this Lipschitz constant of that function also just depends on this interval, because it just depends on the cone. So it's, I mean, let me move that up. So I think this is a tremendously beautiful argument, and it's really elegant, but unfortunately, it's due to Faulkner, not to us. So hence, E square is contained in a rotation of the graph of a Lipschitz function. It's contained in a rotation of a graph of a Lipschitz function. but the graph of a Lipschitz function has Minkowski dimension 1. So thus the dimension of ME squared is smaller than or equal to 1. However, and this is where the last question with 1 comes in. However, this then implies that the dimension of, squared, dimension of E is smaller than the dimension, or actually equal. The upper Minkowski dimension of E squared divided by 1/2. But that is smaller or equal to now by this by 1/2, and that's a contradiction. That's it. Okay. And so I want to point this out here one more time, because that will be crucial when we do this. This is uniform in E in the sense that the only thing that matters is the interval so if you go, let me go here again. This is uniform in E in the sense that we assume that QE is not dense. Q is not dense, and we fix the interval. That QE is missing, and then all the rest of the construction is essentially just dependent on the interval we have chosen here. So if you would have a different set that misses the same interval, the same kind of construction would work to get this kind of higher dimensions. Okay.
Okay, this argument does use this path.
Yeah.
But one can still ask the question whether the Minkowski dimension of E being bigger than 0 would it also give you that QE is dense.
Oh, I see. Not one that I can produce right now. No. Sorry, say again. No, that's just, assuming that kind of, this just assumes that they're not dense. And then you have to get to some kind of contradiction. Right, the cone, the argument would be gross, and the only thing you probably would get is, what would you get?
Only at the end that you use it, you have this,
yeah.
A lot of flexibility in the argument.
Right.
On the other hand, this business that deal with things that are greater than 1/2 in geometric measures that hold up with business comes up a lot. So, for example, if you well ring conjecture, you know that something, if you knew the house door that something was greater than 1/2, then it's very large. We're making
okay.
Probably right, but I don't think you got to say, yeah, by going to some higher dimension, maybe you could do something. I think I tried that. I can't figure out how to make it work.
Right. I think, Laura, I think you have a point in the sense that, there are many open questions around this kind of, if you look at the geometric questions of how these things behave with, when you map them under polynomials. Okay, so as a corollary, just, suppose what this really gives us by the same argument as before. So suppose you have this expansion that does not define Z. And we have that, and E subset or R to the N up to R is nowhere dense. Then the Minkowski dimension, upper Minkowski dimension of E is 0. You do the same argument as before. as we had to take this kind of dense omega orbital set on the left endpoints of the complementary intervals. And we make this closed, but you can also take the closure. Getting all the details. You take the left endpoints of this E, and then if you're positive, you would have positive dimension measure. You would take this Q composed with T, and you map this to somewhere dense. That gives you this dense omega orbital set, and you're done. Okay, so now so this is kind of the unary case, and really now I want to talk about the higher dimensional case, where because for me it's always, so this is about things in the line, that's well, good and well, but of course what we do in definability theory or o-minimality is we want to get some kind of conditions also on higher dimensional sets. And so what I want to do with the last, so many minutes today and then next week is really discuss this kind of what goes into the higher dimensional case. And there this kind of uniformity that we have seen in the construction will be crucial. So really what I want to do is actually not, let's maybe now make this a new section. What I will do is I will consider now the planar case, because that's really much easier. In some sense, some of the kind of technical difficulties are much easier to handle here than in the general case, but the main argument is actually there. So first of all, I should say what I mean by that. So what do I mean by higher dimensional, the planar case or high dimensional cases? If you look at the statement of this result here, of course, if you now would add, replace, if you would change this here and you would add a 2 here, then this would be obviously false, because you have to have, take a line, right? That's nowhere dense in the plane. It's if you bound it here, it's going to be compact, but it doesn't have dimension 0, it has dimension 1. So really what you want to do in the higher dimensional case is you want to state something such that this says that sets have the right dimension. So maybe let me start. I have to go here. Okay, so the higher dimensional K analog, and now I will just do it in R2, is the following. So again, so I state the theorem, and it will take me some time to prove it. So let R be an expansion, and I'm going to fix this essentially throughout this chapter. It does not define the integers. And really the result, and let E subset R2. That's the only thing I want to prove, but we're going to do this true for R to the N. Be bounded, and the sigma. Actually, might only just prove it for closed, but this holds in this generality. Then the dimension of E. So this is really now this kind of topological dimension. So the largest, the projection that picks up interior is equal to the upper Minkowski dimension. From that thing, you actually get also, of course, because the Hausdorff dimension, of course, lies in between those two for all of the, we'll also get equality of Hausdorff dimension. In the paper, we actually prove this. So this I should say is with Chris. We show this actually, there's something, I mentioned this before, but I don't want to go into this. There's this uniform Minkowski dimension, which is called the Assuet dimension, which is a priori larger than the upper Minkowski dimension. And the proof really adjusts also to this more complicated dimension A, because really what we're going to show is in the paper, here I don't do it fully uniformly, is that there's this kind of thing holds uniformly in the families. And so that then gives you that, of course, the equality also holds, because essentially Assoa dimension is some kind of uniform version of Minkowski dimension. This holds also for Assoa. Okay. Good. Now what do I want to delete? Okay, I don't think I'm gonna go. So I will introduce now a couple of things, and then I think I will call it a day and do the proof and finish the proof next week. But the first thing you have to introduce, and because really once you start going to high dimensions, and this might be not surprising for model theorists, is that you need some kind of uniformity. So what I introduce now is not this kind of general notion of uniform Minkowski dimension. I think that we actually don't need for the planar case, but we need a uniform version of being Minkowski noun that I really have to introduce. So this is a definition of some kind of Minkowski dimension for families. Let's say, I really be careful with these things in the bounded and non-bounded case. So let's keep it all bounded for the sake of this course. And now we say the family this family here. There's three here. Is uniform or uniformly Minkowski null. So uniformly has Minkowski dimension 0. Well, if what you expect to happen happens. So if this limit soup k goes to 0 of this thing that computes the Minkowski dimension or the upper Minkowski, when this is 0, uniformly in A. Yeah, so this should be, I don't know why I would k r goes to 0. So again, you can make this kind of, yeah, you can make this kind of, define this for higher dimension, makes it precise what it means to be, you have uniform, better, the family has uniform Minkowski dimension n, or something like that, but this is really not a thing I want to spend too much time on. What I do want to say here, and I want to make, because I was going to make this explicit, is that this kind of projection lemma, that this holds uniformly in families. So I'm going to write this out because this is going to use this. This is 6.2, 6.3 is really now that I'm not going to prove this, but it follows almost immediately from the proof of the original lemma, is that this, you have this projection lemma uniformly in families. So let's call this a uniform projection lemma. Okay. So I'm not sure whether I said this when I introduced the projection lemma for Minkowski dimension. This is the original projection lemma is due to Falconer and Howright. And this is really just an easy modification of the argument. Well, it's really part of the proof, but they don't state it explicitly. So really what this says is that if you have with the family, you have some S, which is supposed to be somehow the dimension that you're going for, and let A, kind of sequences of elements in R to the N, M. So they live in R to the M, and you have some K in N, and they live in, they live in R. I mean, they're supposed to the things that go to 0, such that for all K in N, you know that the number of boxes you need to cover xa sub k is at least rk minus s, right? Yes. So this goes to 0, so you take the inverse so that it gets large. So if you know that for this kind of sequence of a's and this r's, this stays large, then you can find a projection such that the projection also stays large. So far, this is all assumptions, and the kind of now the conclusion I want to write is that then there is a projection, then there's a projection, or it's a linear map really, such that the image under this linear map of this family has the same property with the appropriate S changed to T. So then there is a linear map. So it's really same as a projection lemma, but in a uniform way. Then there is a linear map T from R to the M. I should really use R to the. Maybe the easiest way is to change this to an L. Then so that I get the same formula as before. To the N to R to the M, such that for all A and N, now this is R sub k is larger than R sub k to the minus t, and now t is essentially obtained in the same way as the dimension is obtained in the projection lemma. So that is t is s divided by 1 plus 1 over m minus 1 over n s. So this is kind of the uniform version of this projection lemma. Okay. Okay. I want them to go to 0. So then I'm pretty sure this is true. I don't want to. S should be positive. Thank you. Yeah. Otherwise, yeah. So the dimension. The main point is that this kind of if we want to prove that some final families are uniformly M null, and we want to use the same argument, we have to have some uniformity in the kind of tools that we're using. And you can then this is hopefully the correct statement of the kind of the uniform version of the projection theorem we're going to use. Okay. Right. After I think one more thing that I want to do before I finish today, and this is somehow I have to clean one thing slightly up that I didn't do last time. And so what I'm going to need in order to apply this kind of uniformity is the following uniform version of what I proved earlier. It's really just this was one of these kind of things. Talked this through with Chris, and he guaranteed it's just the pigeonhole principle that I want to do to get this. So remember that we talked about. I need this for next time to make this go through. Suppose you have a subset E of 0, 1 to n plus 1, and this is d sigma. So assuming that we work again in this expansion that does not define the integers, such that EA has empty interior. And so what I showed, what empty interior? What I showed last time was that, last week, I think, was that that there's some kind of uniformity. So what you can do is that you can find an epsilon. You can find an epsilon such that each of these EAs is disjoint from an R interval of length at least epsilon. So I showed them, I can write this out. As I showed last time, there is an epsilon such that for all A in 0, 1, n, there is, let's say, interval of 0, 1 of length epsilon, at least epsilon, such that EA intersected I, this might depend on A, let's say, is empty. So that's what I showed last time, or a little bit ago. And so now what I have to do, what I need is I have to, this is always very dangerous. I mean, this is essentially an existential quantifier, if you let me write it like this. I'm going to switch these to quantifiers, and I claim it's still right. And of course, switching these kind of quantifiers is usually always dangerous, but in this case, it actually really does work. So then there is, or there are, intervals with, I want to call them I1 to IP, subset of 0, 1, such that, so this is a, so that you can compare it, it's not part of the statement, such that for all A in 0, 1, n, the unit interval to the n, one of these intervals, so there is one, there is I in 1 to P, such that now the intersection with that interval, so EA intersected, the notation is empty. Okay. So it's slightly more uniform, right? I mean, so here the kind of, so we kind of fix the epsilon and the corresponding intervals, and then we pick one of these intervals. So it's not a complete switch of the quantifiers, but you have a stronger uniformity than what I claimed. And really, they kind of use all of them. Okay. So I prove this here, and then I've done. Doing this kind of change of quantifiers always gives me panic attacks. So let me try to check whether this actually is correct. So let epsilon. So now we apply this kind of, we apply this one here, and I show you how this gives the stronger statement. So let epsilon such that this holds, so for all A in 0, 1, there is, okay, now I'm writing differently, there is such that length, such that EA intersected I is empty. Okay, so the idea really now is that we apply the Pigeon principle. So now let n be large enough, more or less. So now let n in n positive, such that n is larger than 2 times epsilon to the -1. Okay, and now essentially what we're doing here is we think of looking at the box, and now so we're gonna essentially, sorry, draw boxes here, and those all have to have length 1 over n. And so because we know we have that epsilon is much larger than, because we know the n is larger than this one, we know that whenever I know that each fiber has to miss one of these interval of length epsilon, and this means it contains at least one of these that it misses. So let me write this out. So now let so for p in 0, 1 to n minus 1, we set one more board. We set I p to be the, let it be the closed interval. I think that's fine. P divided by n to p plus 1 divided by n. Okay. And now note, of course, note that the length of this IP is 1 over n, so it's smaller or equal to 1 over 2 epsilon should go here. Right. Let me delete this and I finish this proof. So thus, if you now believe this kind of counting principle, this intervals, so for x, each a now has to miss one of these intervals IP, simply because they're so much smaller than the intervals that we know a has to miss. So thus, for each a in 0, 1, n, there is e in 0, 1, n minus 1, such that the intersection of EA with IP, that's it. So simply by Pigeon Principle. Okay. So what I do next time, I think this is a place I wanted to stop, is I will now prove then kind of that essentially under the same assumptions that I have here. So if you have a family like this, okay, that then this family, so we know that each individually A is Minkowski null. And so what I'm going to show next time is that this family here of the EAs is uniformly Minkowski null. And that is really kind of the crucial case then how you do it for higher dimensions. So then afterwards, what I'm going to do, I will consider the planar case. And really what you have to want to understand in the planar case is make sure that the fibers uniformly are small. And that I will then use to do the planar case. And I'm very confident that I might not finish this on Monday, but by Friday next week. Okay, yeah, this is it for today. If you have any questions. Yeah, so I continue then on Monday.